Okay, so today we're going to talk about Chapter 16, roofing, followed by the extra section that you don't have to do any reading for, but it's about stairs, and it's just because I think it's interesting. So that being said, you should realize by now we've made it through the bulk of the course. So this semester, unlike any previous spring semester, has one extra class day and one extra week. So that extra week falls next week, the last week before class. So basically we have this lecture, we have next week, and then we have the following week is a regular lecture, and then the final. Right? So there's not that much time left in the semester. And so the last day you have your project 3 due, right? Not the day of the final, it's before that. So it's in 2 weeks, project 3 is due. And that day I'll talk about glass, which is chapter 17, and a little bit of chapter 18. That being said, after today and that class lecture, I will have covered everything that I want to cover in the class. So that leaves us with an extra day next week. And so what I'm thinking we'll do is it'll be an optional day for anybody that wants clarification on any topic that we've talked about this semester or on anything outside of what I've talked about. If you want me to talk about something that you're interested in, that's fine too. If you tell me about it up here, I'll put a little sheet so you can tell me what you want. Likewise, if you want to send me an email to gadams@dvc.edu, that's fine too. On any topic you think would be interesting or want clarification on, I really didn't understand moment frames, I'm still confused, let's go over it again, that sort of thing. That's what we'll do next class. So hopefully it'll be helpful, I hope you take advantage of it. I'll see what I can do about putting together a practice exam that you guys can have for that day as well, to make it worth your while. But this is designed to kind of help you guys study and what have you. Does that kind of make sense? Sound good? Okay. So that'll be the plan. Any topics that you're interested in talking about, let me know, and I'll try to wrap this up, or I'll pull slides for that, and we'll go back through it. Okay? Likewise, I'll take the, if everybody says I want to review, if I get multiple emails that say review moment frames or whatever, that will be a higher priority than some obscure, should we use Core 10 in a solved environment or something like that. Right? So, but if you have those kinds of questions, by all means let me know, and we'll go from there. So, the other thing that I'll warn you about, since it's next week is optional, the following week you're coming back for class, is that it's probably likely that there'll be a quiz that last class. And if I were to speculate on what the quiz would be on, it would probably be on, I don't know, let's say terminology of wood. Like if I gave you a light wood frame drawing that was of a window that had some fill in the blanks type questions about it, like where's the header, where's the trimmer, that kind of thing. Does that sound like a reasonable warning? Okay. So, think about that for 2 weeks from now. 3 weeks from now will be the exam. We can talk more about it next week in terms of what it will be. It'll take the Scantron that you used last time. So the 884E, I think. This guy, the two-sided one. Yeah, where's it said? 884E, remember. So it'll take the same one. You'll have the full 3 hours to do it. Typically people are done a lot sooner than that, but you'll have the full time to do it. It'll have the same kind of thing where you'll have the multiple choice true-false questions in the Scantron portion, and then there'll be some miscellaneous questions that you'll write a little bit longer answer for. Okay? That will be the last time for you to turn in any test corrections, so you can turn those tests back in with test corrections that day. You can, of course, turn them in today, you can turn them in next week, or you can turn them in the day that the projects are due. That's fine. Are there any questions about kind of the trajectory to the end of class? No? Okay. Yes?
Are we turning in our notebooks?
That day, so the day of the final is good. I'm glad you reminded me of that. The day of the final, what I'll ask you to do is when you sit down for your test, I'll have you give me your notebooks. It's a really good way of making sure you don't accidentally look at your notes anyway. So I'll take all the notebooks up here. I'll leaf through them. That helps me make up your participation grade for the class. It's kind of obvious based on the notes people take. And of course, I remember you guys being in class or not being in class. But that's kind of where your participation grade comes from. Yeah. If you turn off your notes, that's fine. Just turn those in. No, I have no problem if you printed out the notes and took the notes on top of one of these kind of sheets. and just did your little doodles on something like this, just giving, one of those fat binder clip things, just binder clip them all together. Doesn't matter, they don't have to actually be in a notebook, but try to make them organized. It would help you anyway, because you're studying for the final, to kind of collect them all and put them in one file. So I recommend that anyway. Yeah.
So 2 weeks from today is the project, and then the week after that's final?
Correct.
Okay.
So let me see the actual dates.
So we will not have a test before our project?
No. So the project. So when I originally set up the class, I had the project due the day of the final, and we did it that way. I want you to have the full 3 hours for the final, so that nobody has time pressure on that sort of thing. So that's why I make them do the class time before. But I also gave you a lot of notice that it was coming. So we'll have the first half of class will be lecture, and then the second half will be the project. So and class is kind of fun, and we show examples and whatever. So it's not as involved as some of these other lectures. Okay. Any other questions before we go on? No? Okay. So we're going to start with roofing today, and we'll see how it goes. So we've talked already kind of a lot about high slope roofs or regular sloped roofs. So we're going to start and spend the bulk of the time on the roofing lecture talking about low slope roofs. And so a low slope roof is really what we call a flat roof. And so a flat roof is never actually flat. It would never work if it was actually flat. So it has a little bit of slope. Usually slope is referred to in rise over run, right? Rise being the amount of vertical distance we're going up, run being the amount of horizontal distance. And so a low slope roof is going to be somewhere less than 2 in 12. And that means it's going to go up 2 inches for every 12 inches or up 2 feet for every 12 feet, okay? Or less. Okay, so that's about 17% or less. So the roof deck is the structural surface that supports the roof. And we've kind of talked a lot about that. You should have a good idea of what that would be, but we'll review it a little bit today as well. We also have thermal insulation. Obviously the roof is what's pointing toward the sky, so it's going to get a lot of the direct sunlight. It's going to have to deal with a lot of heating and cooling cycles. So it's certainly something we want to have thermal insulation on. And we also want to have an air barrier, right, that restricts the leakage of air through the roof assembly, right? And depending on the type of roof we're going for, it may be more or less important. And we'll talk about that as we go along. We also have something that's called a vapor retarder or a vapor barrier. I will probably mistakenly call it a vapor barrier. We've tried to switch terminology to be vapor retarder because barrier is a little too strong. It's not actually a barrier. Some moisture can always get through these, but we try to make it as barrier-like as possible, right? Basically, this is essential in cooler climates where you're enclosing a humid space because you'll get condensation, right, on the warm side of the insulation. And so you want to, or I should say, you'll get condensation wherever you have, right, cool and warm coming in contact. And so that's the risky part, and you want to control where that happens in your wall assembly to make sure it occurs in the right spot, not in the wrong spot. And we'll talk about that at length as we go along. And then finally we have what's called the roof membrane, which is the impervious sheet of material that keeps the water out, right, or the snow being water-like, right? Keeps the water out of the building. Okay? We also have to think carefully about drainage. How do we remove that water, right? Especially if the roof has a slope that goes in toward the building, right? A steep roof is not that hard. We can obviously see where the water is going to go, right? If it's a flat roof, we have to think a lot more carefully about drainage to collect and deal with the water that comes off the roof membrane, right? And then we have something called flashings, which prevent water penetration at joints, edges, protrusions. You have a pipe that comes through the roof, a chimney, something like that coming through the roof. Flashing is what's going to deal with that and make sure that the water doesn't penetrate where we don't want it to. Okay? So now we'll expand on each one of those topics as we go forward. We'll start with roof decks. Okay? And roof decks are the thing that we've already covered pretty extensively in the class. If you think all the way back to concrete, which I know seems like it was ages and ages ago, right? A simple roof deck could be a concrete slab, right? Obviously, it's not a slab on grade, it's a slab up in the air, but it's a structural support for the roof. And obviously, on top of that structural support, we have to put the roofing, right? But it could be something as simple as a concrete slab. If we were talking about light wood frame, it would be the platform that would be the assembly of all the joists, or excuse me, it's in the roof, so it would be rafters, right? All the parallel rafters with the sheathing attached to them. That would be, right, this roof deck support, right? Support for the roof, okay? If it was a steel building, right, we might have a structural composite deck where we had that corrugated piece of steel with concrete on top. That would be providing the deck, right? So it varies, and it's based on the stuff that we've already talked about earlier in the course, right? The deck needs to be stiff under expected roof loads, right? So if we're going to get serious loading that's happening, we don't want part of the roof to sag. That would defeat the purpose of the roof. So it needs to have sufficient support to support whatever it needs to support, right? And we're not talking so much about live loads, those of us that can walk around on top of it. We're talking more like heavy air conditioner units and additional things that might end up on the roof, right? Especially things that weren't planned for, okay? The deck also needs to resist the wind uplift, right? Those kinds of forces are very strong on roof environments. We don't want high winds to cause the roof to lift up, and so we have to be able to resist that as well as the downward pressure. Decks need to slope sufficiently toward some drainage point, and that drainage point could be off the edge of the roof. It could be to some internal drain that we're actually collecting the water, piping that through the house, and then getting it out down below, despite all of the structural deflections that might be in the roof, right? So if you put an air conditioner up on the roof and it's really heavy, right, the roof still needs to have sufficient slope to actually drain the water off. What you don't want is for there to be a puddle around the air conditioner, right? And so we need to make sure that it has that. The minimum slope for a roof that's considered to be a flat roof is 1 in 50, or about 1/4 inch per foot, right? So it's really not too much slope, right? That's why we consider it flat, okay? But it does have a little bit of slope, and it does shed the water in one direction or another. So here's an example of getting a roof ready. This is a flat roof, and this would be our structural deck underneath, right? We're seeing sheathing that's been applied here. It looks like it's 1x12s or something like that. I don't know what this building was. On top of this, when they're re-roofing it, right, they put these little tiny sleepers in. If you look carefully, it's narrower here than it is up here. And so they're designing these little sleepers to make just a little bit of slope, right, before we put the roof membrane, right, and or the insulation, depending on this particular roof environment, to make sure that water that falls here is actually going to slope away, right? This is kind of like a little mini ridge, right, or a hip, kind of, that's causing this half to drain that way, this half to drain this way, okay? So it's very subtle, but that's the right way of making sure you have that kind of drainage. You don't necessarily have to do it with a set of sleepers on top of a flat roof. You could adjust each one of the individual joists, right, so that they have a little bit of slope to them. You could shave each one of the joists so that it's narrower on one end and taller on the other end to get that slope. Those two methods take a little bit more work and a little bit more pre-planning than putting those sleepers on after you have a nice solid roof deck. And so it's going to vary a little bit depending on your current conditions, how you're building, and that sort of thing, right? So we can vary the heights of the columns underneath. Let's say this was a steel building, we can vary the height slightly to get that slope. That would be one way of doing it. We can apply flat or tapering insulation to do it, so varying thicknesses of insulation or tapering insulation to try to get that slope. And it can be rigid foam or some kind of lightweight insulating concrete, right? So you could actually put a lightweight concrete deck on top of your structural deck and have that have the slope to it. So there's a variety of ways. The point is, it has to have slope, even if it's a little bit, okay? So why is this a big issue? And so if you have insufficient slope, right, you can have something that's called ponding, right? And if you've ever been in a tall building and looked down on other shorter buildings after a rain, there's a lot of this that happens on roofs, okay? But this is a very dangerous thing to have happen, okay? And so what we mean by ponding is just that when water is applied to the roof, rain, snow, etc., there are areas of the roof that don't have sufficient slope and puddles form, right? And it's like puddles that would be outside, Okay, but these are a little bit worse for what they do to the building. Okay, number one, they can destroy the membranes, the roofing membranes themselves, which leads to leaking and stuff. Which, if you get sufficient leakage, could cause rotting of the structural members and ultimately structural failure. The other thing about it is, as the ponding grows, we're adding a lot of weight to the building. Right? How much does water weigh per gallon? It's like 8.5 pounds, something like that. Okay. So if you start to think about, ponding, right? Gallons and gallons and gallons of water, you're adding weight. Each time the rain falls, right? If it's not draining off, it's adding weight to the building. As that happens, the roof starts to sag, right? And we start to have problems. Make sense so far? Okay. Okay, so we're gonna just walk outside this door really fast, right in the back, and then we'll come right back. Okay? It'll take a couple minutes, but sometimes if you actually see this stuff happen, it'll make more sense.
Okay, so you should, having gone outside and seen that, you should have a little bit more understanding of why we emphasize ponding and making sure that the roof is structurally adequate to hold what it's supposed to hold. So the roof membrane, when we lay it down, needs to be over a nice smooth surface that has no gaps or no little knot holes or no issues in it. So we want to make sure it has a nice smooth membrane, or nice smooth surface to apply the membrane. We also want to make sure there's no nails sticking up, right, which is a characteristic problem with these kinds of flat roofs, right? From my own personal experience, it's kind of a roof. We have a apartment unit that has a deck that's uncovered that is above a parking, like a carport. And this unit was built about 25 years ago. It's actually right where we re-sided that whole side. The deck is made, it has sufficient slope to it, but it's a special material called Gecko deck that's like an epoxy paint that's been painted down over the plywood that has little walnut shells in it for slip resistance, but it's meant to be traffic, right? So it's meant to have traffic, people walk on it, that sort of thing. And because of expansion contraction issues, right? And when it was built, the plywood decking itself, the floor, right, wasn't screwed down. Instead, it was nailed. And so over time, every 3 or 4 years, we'll get one nail that'll pop up slightly. And when that happens, it cracks the membrane. And as soon as that happens, we get leaks into the carport, and it's a big problem. So we have to actively recoat this deck every couple of years and make sure that these little nails aren't happening. So that's to help emphasize why it's important not to have anything that protrudes into that roof membrane, because if there is, you'll get a crack, you'll get a leak. It can be the smallest little crack, and the water can get through, and that then starts to cause all the structural damage that we've seen. So the other thing is that decks need to be dry before you apply this membrane to avoid any kind of moisture complications, mold, that sort of thing. So you don't want to be applying one of these roofing things in the rain, right, when it's wet, that kind of thing. So you want to make sure that the roof membrane is actually dry. Okay? So thermal insulation and the vapor retarder. Okay? The thermal insulation can be installed in 3 places. It can be below the structural deck, it can be between the structural deck and the membrane itself, or it can be above the membrane altogether. Okay, so we have 3 different locations for it, and we'll talk about what those mean. Okay? If we have insulation below the deck, okay, that means we have our structural deck, which would be appearing right here. So this is light wood frame. We have our rafters that are here and here. And we have what would be our traditional fiberglass bat insulation that's in the roof cavities. Right? Each one of those cavities has a piece of fiberglass bat insulation. Notice that it does have the ventilated airspace, right, to allow air to penetrate, right, and run along in between the 2 rafters. Okay? On top of the roof, the structural roof deck, we have the membrane itself. Okay? So the last piece of this puzzle is this vapor retarder, and we're going to talk about where it belongs in the next 3 slides, and hopefully that'll help a little bit more. So the discussion about a vapor retarder varies depending on where we are and where our climate is. Okay? And really what we need to pay attention to is what is the warm side and what is the cold side. Right? And if we're in California, if we're in the Bay Area, the definition of the warm side and the cold side is a little bit problematic, because in the middle of summer, right, or even right now, it's almost May and air conditioners have started coming on, the cold side might be inside and the warm side might be outside. Okay? In the middle of winter, it's exactly the opposite. Right? The cold side is outside and the warm side is the inside. Okay? So California is a little weird, and in terms of where you choose to place something like this, gets a little tricky. Which is why on a lot of buildings around here, we skip this step altogether and we don't put it in, or we use a substitute material like Tyvek, which is designed to be a one-way fabric. It lets moisture out but doesn't let it come in. Right? So it's a specialized material, and that's why we wrap buildings in that, especially in the state of California. If, however, we were in a place like, say, Alaska, okay, typically the way the building works, you're almost always going to be heating the building, right? And so that's going to be the warm side, and the outside is always going to be the cold side. So it's much easier to kind of start to place this. So in a roof assembly like this, that would be in an environment like Alaska, we want the roof membrane, right, to be on the side of the insulation that's the warm side, which would be putting the vapor retarder at the bottom of this insulation, right? And the purpose being that any condensation that forms, any humidity that causes condensation to form, is going to form at that joint between cold and warm, okay? And so cold is everything to here, warm is everything inside, because that's what's being heated, okay? Which is why we want it there. And what we want is we want that condensation to form where it's not going to produce mold and allow moisture into the insulation itself. If we put this membrane up here, the condensation would form here, and that water would get into the insulation, destroy the insulative properties of the insulation, and also cause a bunch of mold inside the insulation, which is exactly what we don't want, okay? If we flip things around, however, and let's say we were in Hawaii, okay, and we wanted the inside of the building to be cold, and the outside of the building is obviously the warm side of the building, or maybe it's the desert, or whatever, some environment like that, we would change the position of this vapor retarder to be on the warm side of the insulation. So all of a sudden the vapor retarder is going to be on the outside of the insulation rather than the inside. Does that kind of make sense? Because we want that condensation to form on the outside of the insulation. So it's going to vary depending on where you are in climate. And that's kind of the important thing to understand. Okay? In cold, this is basically what we talked about. In cold climates, the vapor retarder is recommended on the warm conditioned side of the roof insulation to control where the condensation occurs, right? You can use spray foam depending on the type of insulation and the type of deck that you're going to use, okay? But again, the vapor retarder is still very important, okay? If we have insulation between the deck and the membrane, okay? So if we move up between the structural deck, so I apologize, this picture is kind of dingy, but this is out of the book, so you can reference it, right? The structural deck is here. On top of that structural deck, right, is the insulation. On top of that insulation is the roof membrane itself, okay? So in this environment, right, the insulation is going to protect the deck itself, the structural deck, from any temperature extremes, which is good, right? So we're not going to get weird expansion and contraction issues on the material itself. Not so much for wood, but maybe for a steel environment. And so that, and then it's also going to be protected from the weather by the membrane, right? So it's going to be protected from rain. Okay. In cold climates, remember the vapor retarder needs to be installed below the insulation, which is a little bit complicated. So we need to have that vapor retarder, right, that's installed below the insulation, right, which would be right in here. Right, which is a bit awkward in terms of where you're going to place it with that insulation. So what you'll end up doing is you'll have a special inline vent, right, something that looks like this, that will allow that moisture to come out. Right, so we have these specialty vents that'll be put in for this kind of a situation. Okay, and that's just basically to get rid of any moisture that might happen, that might condense. So where you put that vapor barrier now again varies. Likewise, if we switched climates out of, I'm going to stick with cold for the most part, but recognize if we switch to Hawaii, we'd have to change the placement of the vapor retarder, sorry. Right? What about putting insulation above the roof membrane, right? And so this happens, it's usually called a protected roof membrane, and what that means is that the membrane itself is going to be protected from temperature extremes. So we no longer have the extreme hot, the extreme cold right on the membrane. We've got the insulation in there, right? And it also means that the membrane itself is acting as the vapor barrier. Because it's a waterproof barrier, we don't have to worry about a vapor retarder or a vapor barrier, right? So that's also an advantage. The disadvantage, right, is that the material needs to retain its insulating properties when it's wet. Right? And so fiberglass bats are the worst example of something like that. You lose almost all insulating value if the fiberglass bat gets wet, right? Which is why if you have severe water damage or a flood in your house, you're worried about that insulation, you're worried about getting it out and replacing it with new insulation, right? So we need to make sure that that insulation can be exposed to water and doesn't degrade when it's exposed to water. Some types of foam are fine, other types of foam are not. Right? And they might soak up water or resist the water, right? The other thing is that the membrane can't decay or disintegrate when it's put out in the sun, right? So if you've played around with foams, some foams you stick out in the sun and they start to deteriorate in the weather. Some foams retain their rigidity and retain their insulation properties. So it's going to vary a little bit. So this is an example of one of these assemblies. Sometimes they'll put this little skin on it that'll help with sun, and it also will help with traffic so you don't accidentally dent it or destroy it. There's our insulation. Down here is our roof membrane, and below that is our roof deck itself. Okay? So, in terms of thinking about rigid insulation as a material, it should have high thermal resistance. Obviously, the point of insulation is not to allow the heat or the cold to come into the building, so it needs to have high thermal resistance. It needs to have adequate resistance to compression, denting, gouging, decay, and fire. Okay? So this shouldn't be too hard to imagine. If you walk out on it and it compresses, that defeats the purpose of the insulation. So it needs to be able to support some weight. And it also needs to have high resistance to melting if it's not part of, if it is part of some kind of a hot applied roof membrane itself, which we'll talk about in a second, right? So if you're applying a hot membrane as your roofing material and you put this insulation in, it can't melt. So it needs to have that high heat resistance, right? So, in a low slope roof, there's typically 2 layers of an asphalt saturated roofing felt, right? Which I'll pass around an example that are adhered to the roof deck with hot asphalt, right? And so this is acting as the vapor retarder in this low slope roof. You can use what's called the self-adhering bituminous membrane, right? Which is also very, very common. So this here, right, would be the self-adhering membrane, right? And so when I pass it around, go ahead and peel a little bit back, and you can see that it's self-adhering, it's sticky, right? So this would be a cold applied system, right? I can take a roll of this, I can peel off the backside, and I can stick it right down to my deck. So that's cold applied, right? It doesn't require any heat, right? Or we could have roofing felt. That's probably the best example. Right? A piece of roofing felt is an asphalt impregnated felt, right? So think of asphalt like we drive on asphalt, it's a distilled petroleum product, right? It's been saturated into a felt. So we're taking 2 layers of this with some very hot asphalt at the same time, right? And we're applying those 2 layers together to create this membrane. Does that kind of make sense? Right? So I'll pass this around so you can see that. But we're going to talk about it in far more detail as we come up here. Exactly, and that sticks the whole thing together, and that would be considered a hot applied application, right? Because you have to heat up the asphalt to be able to cause them to stick together, okay? So, the vapor retarder must be located within the assembly on the warmer side of the insulation. We should have gotten this by now, okay? Except on a corrugated deck, where you need some kind of a substrate board across the decking prior to the application of the vapor retarder. And so I don't know that I actually have any vapor retarder up here, but you guys are all familiar enough with plastic to kind of know what I mean, right? So you can think of it as a sheet of plastic, okay? There are smart membrane materials that allow some water to penetrate one direction, but you guys get the idea, okay? So generally speaking, membranes are going to fall into 3 different categories. There's the bituminous roof membrane, there's the single ply roof membrane, and there's the fluid applied roof membrane. And we're going to talk about what they all are and what the advantages and disadvantages of each of them are. Okay? And so we'll start with what's considered to be the built-up roof membrane. And it's assembled in place from multiple layers of that asphalt impregnated felt. Okay? And so this one, we keep losing some of our ballast on it year after year as it's being passed around. So be somewhat gentle with it. But this is the best example of kind of seeing those layers built up. Right? So this is a piece of roof membrane that's been cut out. And if you look carefully at the side, you can start to see the various layers of that asphalt felt. Right? And then on the top, this last surface, which is rocks, is a ballast, which we'll talk about in a second. So pass this around, but it can help you kind of see the thickness of these layers as they start to come together. Okay? And so the felt that we're going to use, like the sheet that I passed around, is delivered to the site in a roll. right? And the width of the roll is going to vary a little bit depending on the equipment to be used, but it's going to look something like this, right? And in this place, in this particular example, they're actually loading into a machine that will help roll it out, right? Which definitely assists the process, right? The bitumen, right, is usually an asphalt that's derived from a petroleum distillation process, right? And so it's not the asphalt that we think about that's out on the highway that has rocks already embedded in it. It's more of a liquid product, right? That's going to help these layers adhere together. It's applied hot in order to merge the saturant that's already in the felt itself with the new saturant that we're putting in, right? So it's basically like saying you have something that's already filled with glue and you add a little bit more glue to bind the two together, right? It forms a multiply membrane, right? And the felt is applied in overlapping layers, which is important to make sure that the seams overlap so you don't have a crack that goes all the way through. It's kind of like shingling in a way, right? Typically a membrane is going to be anywhere from 2 to 4 plies in thickness, right? And a ply is just one layer of these, okay? The last piece is that there's a layer of crushed stone or a layer of rolled roofing that has mineral aggregate that's already put in it, right? Something like this. That provides a protective layer on the top surface, both from the sun, right, and from potential traffic. And there are other ways of making sure the traffic areas are more protected, but you want something on top of that roof that's going to protect it from its traffic, all right? And so let's look at the actual drawing, right? And so in this particular installation, right, we're putting our asphalt, here. You know, sometimes you get so tongue-tied that you just can't get out what you're trying to say, right? Okay, so in this particular example, we have a concrete deck, right? That's our supporting surface. On top of that, we have an asphalt primer coat, which is basically a hot asphalt that's been applied to the deck itself to kind of seal it up and give us a good surface to adhere the felt to, right? We're going to lay down an overlapping layer, right? Layers of this felt, right? On top of that, we're going to put in some more asphalt. Then we're going to put our rigid insulation boards down. And then on top of those rigid insulation boards, we're going to put an aggregate on top. Right? And so this particular assembly is where the roof membrane, all the layers of felt, are below the rigid insulation. Right? So this is where the insulation's on top. When we move on to the next slide, right? Well, I guess I don't have, we'll see that slide in a little bit, right? We have some other options that are also available. We can use a modified bitumen roof membrane. It's manufactured in a factory from sheets of polymer that have been like modified. I think I have an example here. These are single ply. Well, okay. It's a lot like something like this. This one doesn't have the adhesive on the backside, but it's a lot like something like this, where instead of a felt, right, it's actually a synthetic product that's stronger and more water resistant, right? But we can swap that out for the felt, right? So it's not going to be a hot applied system, it's going to be a cold applied system. But you guys get the idea. I apologize I don't have one. I thought I did have one, but I don't. So this increases the flexibility of the material, right? It allows it not to crack as easily, right, in different temperature extremes. So it's a little bit more of, it's like switching from regular wood into an engineered lumber product, right? We're trying to use our knowledge of technology to improve what we're actually using. So it's a little bit tougher and that sort of thing, right? So here's our rolls of felt again. Right? We're applying them in overlapping layers, like I talked about. The layers can be torch applied, they can be hot bopped, or they can be cold applied adhesive or self-adhered. Okay? And so what do each of these mean? Okay? And if we take our roll of this bitumen, something like this, one side of it could already have some, so it's like taking this piece of felt, right? One side of it could already have an asphalt that's been put on it, that's been allowed to cool, right? So you can handle it and roll it out, okay? But when you roll it out, as you roll it, you take a torch
right? It's usually hooked up to a propane tank, and you flame that side of this that already has that cool bitumen, that cool tar, so to speak, on it. You flame it to heat it up, and then as you apply it, it glues itself together again because you reheated it. Okay. The other thing is hot mopping is where you take the liquid asphalt itself that's hot, right? You spread it out, and then you apply these layers together. Okay? A cold applied adhesive is something that can be applied without being hot, but that will cure through the process of like an epoxy or something, right? Where chemicals combine and they seal it up that way. You could think of like a caulking or something like that comes out of the tube in a liquid form, but then ends up solidifying into a solid. Okay? Self-adhered would be like that sheet that I passed around earlier where it already has a sticky backing on it. Right? So we're just sticking itself, we're peeling the backing away and sticking it down. Okay? The cap sheet is the topmost layer and it's surfaced with mineral granules. Right? Something like this. Oh, this is actually a pretty good example. Right? So this one is a self-adhered. Right? So it looks like what we saw before. Right? It's like a felt with the granules on top of it, but it has a sticky backside to it, it's going to stick down so it's cold apart. Okay? Obviously, be careful of this stuff because it will get on you. And your clothes, and your shoes, and everything else that it might come in contact with. All right? Okay, so here we have an example. We'll walk through it. In this case, we have a corrugated steel deck. We have a first layer of rigid insulation boards. In this instance, they're mechanically fastened to the steel deck itself to make sure they stay in position, right? After we have that first layer that's mechanically fastened, we'll put a layer of asphalt down and then put our second layer of rigid insulation boards. So it gives us 2 layers, which is nice. The asphalt is acting like the glue in this case. It's gluing the 2 together. We're covering up all these fasteners, okay? Afterward, we're applying our next layer of asphalt, right? Followed by all of our felts, building up those felt layers, and then we're putting a layer of asphalt plus our aggregate on top. So this top portion to here is like the board that I passed around to you, right? It has the aggregates on top and has about 4 layers of the felt that's been applied.
When you're designing your units, are you choosing what type of roof you're going to do and what type of insulation before you even, or does that happen during construction?
It should happen. It's a good question. It should happen before, right? Because you as the architect, you as the engineer should have a knowledge of what type of roof you're going to do because it's going to vary a lot in the construction process. If you're going to be doing batt insulation on a light wood frame, you're going to be doing the roofing one way. If you're going to be doing something like this where you have corrugated steel, you're going to be doing it differently because of the surface that it's presenting to you, right? If we had a slab surface, we'd be doing it differently. If for example, it's a slab, we have no cavity to be able to put insulation below the deck. Okay, so we have to put it on top, and then it's a matter of deciding, do we want it to be underneath the membrane or on top of the membrane, right? And that could depend on what you're trying to do, right? What product you're trying to use, right? Which you probably would specify. What look you're going for, how much traffic is going to be on the roof, all of those things that kind of come together. And so you as the designer should probably decide that in advance. Okay. That being said, probably not 100% of the time is it decided. You could get to the point where you hire a roofing contractor and they just do it, right? But it depends on the scale of the project, right? If it's a large project, it's going to be decided ahead of time. So the other thing that we can do is instead of having these multi-layer, multi-ply assemblies, we can have something like these that I'll pass around in a second, right? Which are single-ply roof membranes. Right? I'm going to keep this one. Okay? And so they have some serious advantages. It takes a lot less labor to roll out a giant sheet of this single-ply roof membrane across the entire roof, fasten it down, and move on. Right? We don't have all these layers that are coming into being. Right? It's also very, very strong, very durable, and very elastic. It works as a sheet, right, that almost floats across your roof. It's kind of like covering your building in plastic, right? But if you look carefully, especially that one which has fuzzy edges to it, right? All of those are nice strands, either of fiberglass or another very, very strong material in tension. And we'll talk about glass next week actually being stronger than steel in tension.
So you're using a lot of really strong materials to engineer this roof membrane. So it's a lot stronger. That being said, there are some serious disadvantages, right, to using something like this as well, right? It needs to be affixed to the roof by either an adhesive or some kind of a ballast or some kind of a mechanical fastener, okay? And so if we're using adhesives, the adhesive has to be compatible with whatever this roofing membrane is, right? We can't use hot asphalt if the single-ply roofing membrane isn't resistant to that heat, right? We have to know the chemical composition such that the chemicals in the adhesive don't degrade the membrane itself, right? If we're using ballast, right, by ballast it just means you're covering it with rocks or something to weigh it down, okay? You run the risk that those rocks or whatever have something in it that could puncture this single-ply roof membrane, which is problematic. Obviously, you don't want it to be punctured, right? Or you need to use some kind of special fastener, and this is where it gets a little tricky because you've got some fastener that's attaching this to the roof, which is a potential point where it's going to leak, and so you have to deal with making sure that it doesn't leak, right? So we have thermoplastics, right? These are sheets that can be seamed with heat. They're designed for that. We have thermal setting sheets. These are seamed with a liquid adhesive or a tape or something like that, right? Because you might not get a complete sheet that can cover your entire roof. You might have to piece them together, and so you need some way of doing that. So the big problem with something like that is that there is only a single layer, right? So if something were to happen to that topmost surface, right, that membrane itself, some little nick, you don't have any redundancy, right? If you have a multi-layer, say 4 plies of roofing felt, right, something happens to the top layer, not the end of the world. You've got 3 more layers that are going to help stop the water, right? If you have something like this that's only a single ply, you have to be much more careful about any kind of a little nick because that could really cause a big problem instead of a little problem, right? So one more note about those single-ply roof membranes. I did one job that had one of these single-ply roof membrane roofs on it. Jonathan, you have a question? They're designed not to be applied in multiple layers, right? And part of that is how do you glue them together in the first place? Because they're not like an asphalt impregnated felt where it's easy to join them together, right? That's where you can feel in walking around. They're designed to be separate. So anyway, I did this one project where we had one of these roofs, and we needed to cut a vent through the roof to exhaust the dryer. We were putting a laundry room inside, and the only way to vent this particular laundry room was part of a 4-plex. It had to vent out through the roof. That was the specification that the city gave us. So anyway, we had to cut through this membrane, which is an inherently challenging sort of thing because the point of having one of these nice seamless membranes is not to cut through it. And so we ended up hiring a roofing contractor. Even though normally we would deal with the roofing all on our own, we hired a roofing contractor out because it was this kind of specialty thing. It was a special membrane, and they had to come out and deal with it and work around it with other types of this membrane that had the right kind of thermal setting properties to be able to seam it in. But it's the kind of thing that makes me really nervous, just having this one membrane. Right?
What does the person choose?
It could be cost, right? Yes, it costs a little bit more, but the labor cost is much less. Sorry. Clearly I forgot to put my phone on vibrate. It could be a cost thing because you're only doing one layer and it's an easy thing. It could be that somebody sold somebody on it being a really innovative good product, right? And they want to do it for that reason. It could be the complexity of the roof just warrants it. It could be that the lack of complexity in the roof because it's so simple that it makes it a really good option for a single sheet, right? So it's going to vary a little bit depending on the building. So it's hard to say there's one reason you choose it over another, right? And there's certainly a large amount of it that would be, a personal opinion of whoever's doing the designing of it, right? And the tolerance of risk, I guess, is what I would say, right? So the other type of roof membrane that can be applied, right, is a fluid applied roof membrane, right? And this is used for complex situations, domes, shells, curving surfaces, where it's difficult to apply a sheet good. And the point of something like this is that it's installed in a liquid form. You're either spraying it on or you're rolling it on, and it usually takes several coats, right? And these epoxies, basically, are what they are very, very strong, very durable. They can work well as a roof membrane. The only challenge with something like this is that they require very frequent maintenance. And so this fluid applied membrane is what I talked about earlier on that deck, right? That every 4 or 5 years we have a leak. What we really need to do is about every year we need to go back and apply another set of coats. The problem is you have to get up there, you have to pressure wash it, you have to clean it, you have to scrub it down so it's ready to adhere, right? If it has any dirt on it, the next layer is not going to apply to it, right? Which means everything has to be removed from that deck. You've got to get it perfectly clean. Then you go ahead and apply that next fluid coat. You put in this particular example, it's a little granule, it's a walnut shell to give it a little bit of texture so that when you walk on it you don't slip, right? And then it gets dirty, you let it dry, and then it gets dirty again, and you have to clean it and do the next coat. So it's a bit labor intensive from a maintenance standpoint long term. It's pretty expensive as a product too. A 5-gallon bucket of this stuff is about in the neighborhood of $500. So it's relatively pricey, but it's relatively easy to apply. So it has its advantages, it has its disadvantage. Okay? So if we're ballasting or trafficking on a particular deck, we need to be able to cover that roof membrane, right, so that it can be weighed down, right, so that it doesn't lift up in the wind or something like that. And so we're going to cover it with some kind of a loose, very rounded stone. That's a key term because we don't want it to have any sharp edges on it because that could defeat the purpose of the roof membrane. So it's going to be nice, rounded stone. It could be covered in some kind of a concrete paver block system, which could be good if you were, inhabiting this roof deck for some reason. And so this holds the membrane down from wind uplift. It protects it from ultraviolet light, which is also good, and it protects it from physical wear, right? Because that's actually a pretty big problem, right? So if we have a place where we're trying to make a rooftop garden or something like that, we need to cover up this roof membrane with a material that allows us to walk out on it, right? And so that's what a traffic deck is designed to do. It's designed to give you a walking surface. There are always little cracks in the surface, so if you look at something like this, these little gaps in each of these paving stones allow the water to penetrate through to the roof membrane where it can then flow and go away. Okay? So the water is going to fall between and through and around those decks, right? There are usually special blocks that are either concrete or plastic that hold the paver stones up off the deck to allow it space to flow, right? So that it doesn't cause damage to it. The only problem that I've seen with this sort of thing is if any debris, any little leaves, any little particles get in there, you can end up causing little dams and little problems underneath all of these paver stones that don't let the water flow as freely as you would like, right? So sometimes there is periodic maintenance where you'll have to be able to pull these up, clean that out underneath so that they can continue to flow, right? Because the last thing you want to do is have a whole bunch of little debris that's causing a puddle, right? Ponding to form, which we all know is a bad solution, right? So we'll go through a variety of little examples here talking about edge conditions and what have you, because this helps to see how this stuff is made up, right? So this is an edge condition here. We have a curve that's built up on the side, making sure that the membrane itself is going higher than the surface of the deck, right? This is important in this instance because we're not trying to drain to the outside, we're trying to drain to an interior drain, and we want to make sure that there isn't an edge that can cause a crack or some kind of water penetration, right? So we come up so that we have plenty of space here that's not allowing the water in. Notice all the roof membranes that have been applied together, plus an extra layer that's right on this top surface here, right? Then we have a piece of flashing that's right over the edge itself, right? So we're controlling the water so that water that would fall here is going to flow down into the roof, right? And this edge is covered on both sides. This has that little metal drip edge like we talked about last week to make sure that the water drips away from the building itself, right? And so this is a special little clip that holds it down into place. This is at a scupper detail, right? On these kinds of buildings, and chances are you've probably noticed this, you just probably haven't paid that much attention to it. What we're talking about here is a place that's deliberately cut, right, at the level of the roof deck that can allow water to come out, right? And they'll have like a little decorative piece that'll be a downspout that'll collect the water from the scupper, and it'll come down the side of the building, right? Or it'll have just a little square piece that extends out and allows it to drip off the edge. Just depends on how it's designed. So this little low point, right, is where water is actually allowed to flow out. And so the way this is built up is slightly different. This roof should slope toward this point to make sure that the water can actually get out, right? Wouldn't do you any good to have this scupper cut in that's higher than the roof deck itself. That would defeat the purpose, right? So it needs to be low enough to get the water out. Notice that this piece of flashing goes underneath this layer of felt to make sure that the water that's running across here will continue to run over the piece of flashing and not get caught underneath it, right? Okay. Another example of this is a proprietary roof edge system. It's a little bit smaller, doesn't require all that block, but you can see that we've got this going underneath, right? And this looks like a form of insulation, right? And then on top of this, there'll be a bit of a membrane that'll bridge that gap. All right, and so there's plenty of proprietary systems, and they're going to vary. If we have a building separation joint where we have two adjoining buildings or two pieces of buildings that come together, right? Think San Francisco row houses, those kinds of things. We obviously need to deal with how the roof decks come together. And so in this case, each side is going to build itself up to a little sub-wall, right? And then on top of the wall that comes together, there'll be a little piece of flashing, right, that caps the wall and keeps water from penetrating down. Any water that were to fall on this side would hit this little metal drip edge, drip away, and then run down into the building itself, the roof itself. Right? Likewise, any water that's hitting here is going to flow down into the roof surface. Same on the opposite side. This little thing, that's a compressive joint, and so this is designed for expansion and contraction of the buildings. Sometimes this can be even a little bit bigger because it's designed for seismic separation of two halves of a building. It's going to vary. There isn't a good example around here of a good seismic joint. There's a lot on the Berkeley campus where if you're walking through two buildings, the architecture building's a really good example because there's a tower on one half and there's a 4-story building on the other half. And right where the two buildings meet, there's a seismic joint that runs all the way through the building. And so you can walk around and you can see where that joint is and how they're separating the building, but still dealing with these kinds of waterproofing conditions. In this particular example, I'm not sure what they're using it. They're calling it compressive insulation of some kind. It could be something that's fiberglass, it's compressive. It could be something more rigid than that. But it's something that's relatively resilient. So if the two buildings were to get closer together, it would compress, and then when they got further apart, it would stretch. Right? So it's designed to be something like that, but it doesn't specify more. If we have an area divider, this is on a larger building where we're trying to get parts of the roof to slope one way, parts of the roof to slope the other way. This is a way of actually dividing the roof into sections. Not necessary. You could have the roof where it just slopes one way and slopes the other way. Just depends on who's designing the building. And so this is very much similar to the building separation joint that we just saw. It's a little vertical wall that has a cap that's over the top of it, making sure that any water that were to fall goes to one side or the other side away from the joint. Okay. This condition is a little parapet wall where the wall extends up beyond the surface of the roof. Right. This building would be a good example if we walked outside, not the little gap, but further along. This is the kind of thing where I'd love if we could all go up on the roof and we could talk about it that way, or at least go into a tall building and look down on the roof, but we don't have that option right now. So in this particular example, we still have a metal cap, a little flashing cap that goes underneath the decorative concrete top of the wall. That flashing cap allows any water that were to penetrate through the grout lines, little cracks, that sort of thing, to make sure it runs to one side or the other. There's our drip edge. It's on top of the multiple layers of asphalt, making sure that any water goes into the roof membrane and not into the wall itself. Proprietary parapet cap. This makes me nervous because there's no waterproofing at all applied to this wall in the little drawing. My guess is it's just demonstration of how it would work. Okay. If we have an interior drain, in this particular example, it's a conventional cast iron interior drain. The best thing to think of here is it's kind of like a shower drain, right? If you're in your shower, taking a shower, and you look down, obviously the water needs to go somewhere, and it needs to be waterproof to get into this drain, and then it needs to go out and travel through the building. And so in this example, we're doing the same thing. It's like a giant shower pan, right, where we're draining to this one point. This strainer is just designed so that the leaves don't collect in it and get clogged, so that it will drain. The worst case scenario would be leaves to get clogged. This backs up, causes ponding on the roof, leaks out one of the joints somewhere. That's exactly what we don't want to have happen. Okay? If we have a vent pipe, remember last week we talked about waste plumbing and those kinds of things needing a vent that comes up through the roof membrane itself. We have to make sure that we frame around something like that. And so again, this is in the flat roof environment. We're using the same strategy that we would at one of those area dividers or building separation where it's a little bit of a wall. We're doing the same thing here with a sheet metal cap that's going around it to make sure anything that falls on and around this drain is going to drain off and onto the roof membrane. Okay? So there is structural metal roofing for low slope roofs. We're talking 1/4 and 12, something like that, so 1 to 50. It has sufficient stiffness due to its shape to span between purlins without the need for structural deck beneath it. It's kind of a proprietary sort of thing, but it's at least out there, so it's important for you to see it. Okay? We'll move from there into steep roofs. I don't have as much talking about steep roofs today because we talked a lot about them in last class. So a lot of the edge details and those kinds of things that we talked about are the same, so I don't want to repeat myself again. But we'll talk a little bit about roofing the material a bit more. So there's 3 typical categories. The first would be a thatch, the second would be shingles, and the third would be an architectural sheet metal. Right? Now we'll talk about what each of those are and how they work. Okay? So, insulation and the vapor retarder are usually installed below the roof deck in a sloping roof, right? And so if you climbed up in your attic, chances are it looks something like this. If you have vaulted ceilings, it would be in the roof cavity, but generally the sloping roof environment is going to be a light wood frame or a heavy timber frame building, right? It's less likely to be Trader Joe's or something like that, right? A steel building or a concrete building. Doesn't mean it can't happen, but it's less likely, okay? The underside of the deck is usually left exposed. If it is, then a vapor retarder and the rigid insulation can be applied above the deck and below the roofing material. And so you might apply this in between, and I have a good example on my house. I have one set of the building that has a vaulted ceiling. It's in the living room. When they redid the roof, thankfully this is before I bought it, they actually did add rigid insulation. When the house was built, I guarantee you it didn't have it, right? But they went ahead and did it. In that case, it's not exposed underneath, so you have to be careful about where that vapor barrier exists. I don't know if they installed it correctly or not, but it seems to be working, which is good. But on the rest of the house, right, we have the insulation down below, so the vapor barrier is going to be inside the building if it's there at all, not up where the roof membrane is. Okay, so just remember to always think on the warm side, and you'll be okay. So, shingles can describe wood shingles, shakes, asphalt shingles, slate, clay tiles, concrete tiles, right? Shingles is just kind of the generic term for that. Doesn't mean it's all these little tapering wood pieces, right? They don't have to all be this. Right? They're applied in small units in overlapping layers with staggered vertical joints, right? And so this just means that every one of these joints is always going to not fall on one of the joints below, right? And whether it's concrete tile roof, whether it's a wood shingle roof, doesn't make any difference. It's applied the same way. So wood shingles, right, are thin tapered slabs of wood. This is the only example I have here of just a plain old raw shingle. Unfortunately, it has a scalloped end to it, so it's not quite what I'm showing you here. But you guys get the idea, and I will pass it around so you can see that. It's tapered. It's sawn from the tree trunk with the grain running parallel to the face of the shingle, right, which is important. Ideally, it has no knots. It's perfectly clear, which that one is, because if you had a knot, there's a point where water is going to go through, and that's exactly what we don't want in a roof environment. Shakes, right, instead of being sawn from the wood, they're actually split from the wood. So they have a much rougher texture, and they kind of have a little bit different look. There are still roofs like this that are floating around from the mid-50s. Sometimes they can be shingles that have just weathered a lot. but most of the time they're actually shakes that have been split. Shakes usually are a little bit thicker than shingles would be. That's a typical shingle. It's much narrower, maybe a 1/4 inch, at most 3/8. Something like this can be in a 1/2 and larger, right? So it's a little bit thicker. And look, so it has a different texture, okay? So usually, right, this is made from some kind of a decay-resistant wood. It wouldn't make sense to use wood that wasn't decay-resistant. That's kind of the point. It's exposed to the weather. We need that decay resistance. So it's going to be redwood. It's going to be a red cedar. It could be a white cedar, right? It could be a Chinese cedar, which is not actually part of the cedar family, but it's still decay-resistant, slightly different. And it's recommended to be applied over either a breather mat, which I'll talk about, all right, or some kind of a continuous airspace underneath. So if you have an older house and you still have a shingle roof or a shake roof on it, and you climb up into the attic, you'll see what's called skip sheeting, right? And it looks something like this, where instead of having a board that's continuous across the sheeting of your roof, like we would do today with an OSB or a plywood, right? You have boards that run, right, in a certain region, then there's a gap, then there's another board, right? And so when you're applying this, right, here's one course of shingles, it's being nailed to this board, right? When we move up and we apply it, it's being nailed to this board, that one's being nailed to that board. You kind of get the idea, okay? But it's allowing air underneath the shingles to allow the building to breathe. So you don't have one side that's exposed to the weather and the other side not being exposed. If we were on a building that had a vaulted ceiling, we were on a building that was built today that had a roof sheathing that was applied, you'd use some kind of a membrane. It's not really a membrane, it's more of a mat, right? That would allow for this ventilation. So here's a little bit, I have a picture on the next slide of this membrane. The only thing I could find are waterproof membranes for a foundation, but it's similar in concept, right? It's a little bit, it's something like this that's made of kind of an expanded mesh that allows air underneath the shingles, right, to allow it to breathe. Okay, but these aren't. I'm not going to pass these around because it's not actually the product, right? But it's very similar. So, next slide shows you a little bit better picture. Here's a picture of that stuff. It's kind of like an expanded spun plastic.
Brillo pad.
Yeah, something like that. And so this is designed for that breathability, for that air to be able to pass through and make sure that the undersides of the shingles can dry out if they get wet, or that sort of thing, right? If we move into asphalt shingles, no, apparently I don't. Oh, here's the color spectrum of asphalt shingles, right? So you can see a variety of these in a variety of colors, right? So I will pass these around so you guys can see that, right? They're die cuts from sheets of the asphalt impregnated felt like we talked about, right? They usually have the granules applied to the surface of them, right? And when I say that they're die cut, right, they're designed to look like shingles, right? And so the simplest shingle is going to be a 3-tab shingle where it has 3 cuts along it, right, to make sure that it kind of looks like a shingle, right? And it's just going to be the lower section has those cuts on it. It's going to glue in with the rest of the assembly, and when you layer them up, it looks like kind of a shingled look. As you move into the thicker shingles, right, with thicker butts, what they're doing is they're layering up multiple layers of this product, right, multiple layers of felt to give it a little bit more texture, make it look a little bit more like a shingle roof would look, right? And so you can change the look of it based on the thickness of the material itself. It usually comes in a 12 by 36 inch sheet, right, which is very, very heavy. Anybody ever done this kind of roofing? Yeah? Carrying a bundle of this stuff is ridiculously difficult, right? Which is why you try to get rooftop delivery. So it shows up on top of your roof so you don't have to climb up with these bundles of shingles. They're very, very heavy. And that's certainly something to think about when you're designing the building frame. That would be something that's dead load, that's adding to the weight of your building itself, right? So it's designed to make it look kind of like shingles. Depending on the grade and the quality, it's going to look more or less like a shingle in your look. It's pretty inexpensive. It's pretty quick to install. It's moderately fire resistant, So if you had a burning, you were in a wildfire and you had a burning ember that landed on your roof, it's not going to be as bad as a wood shake roof, right? But it's not going to be as good as a concrete tile roof, right? So it's somewhere kind of in the middle. It says it lasts 15 to 25 years. You can buy a 30-year roof. You can buy a 50-year roof. Those numbers are completely bogus, right? You cut the number that it says in half at a minimum, and that's kind of what you're looking at. This is one of those things that's a great illustration of how marketing works, right? So let's say you buy a 30-year roof, and it's guaranteed for 30 years. What that guarantee is basically saying is we will refund you a portion of what you paid for the roof if it fails before 30 years. But that refund is not the whole what it cost you for the roofing. It's a prorated amount based on how old the roof is. So if the roof fails at 15 years, they might give you a quarter of your money back, okay? Which doesn't really help you in the grand scheme of things because, yeah, okay, that means you're going to buy more roof. Well, chances are you're going to buy more roof from them, right, or a similar company. And when you buy that roof, you have to pay somebody to install the roof in the first place. So they're not refunding any of the labor that's involved. So just because you buy a 30-year roof or a 45-year roof doesn't mean that you're off the hook for 45 years. It doesn't really work that way, right? So something to be aware of. And the thickness certainly helps in the durability and the wearability of a roof. So the thicker the roof, generally the better. But it does have a lifespan. It is the kind of thing that you're going to end up replacing. Right? And it certainly depends on the quality that you buy in the first place. It is applied, I forget whether the next slide shows it. Yeah. So, in this particular instance, remember we still have to apply our drip edge that we talked about last class. We don't have a blow up of what that would be doing. Right? After that, we roll out our roofing felt. Remember, we always start at the bottom of the roof and we work our way to the top of the roof, to the ridge of the roof. Right? So we start at the eave and work our way up to the ridge. They always overlap, every layer that we put on, right? And we'll start in one corner with what's called a starter roll. And a starter roll is half of the shingle. It's the back half of the shingle. And we put that down so that it has enough thickness on that lower portion, right? Because otherwise we have a single layer here instead of a double layer. Everywhere else we have a double layer. So we start with that starter roll. There it is. It has a little bit of glue that's pre-applied to the bottom of the roofing. I thought I had one of these. It's really bugging me that I don't have one. Hold on. We have lots of samples. It's glued in. So this tells you that the stuff actually is very sticky, right? So anyway, this is a very poorly put together roof, but here's what we're kind of talking about with that membrane that's underneath. This one isn't even an actual shingle, so it's showing you. But it should have these little bits. We're going to put this away. So poorly put together. So we'll get rid of that. Pretend like it didn't happen. Right? So we'll go back to the drawing. So on one of these sheets that we put down, it has these little bits of asphalt glue, so to speak, that have been applied on the sheet so that when the next layer lays on top of it, it helps to glue the shingles down, right? And so in order for that to heat up enough to actually weld them together, you need kind of a nice hot day. So it's not the kind of thing where you're going to apply a torch to it. You just want a nice hot day, and they'll glue together. So you start with this first half roll, which is called the starter roll. Then you lay your first set of shingles, right? And so you start in a corner and you move your way over. When you move to the next set of shingles, you want to start with a half of a sheet, right? Because you want to make sure all of the joints are always staggered, right? So you start with that half of the sheet and you continue along, and pretty soon it could be, you could start with a half, you could start with just one little quarter, it depends. Pretty soon you're going to end up with a staggered pattern that looks something like this as you move along, right? And so you continue to work your way up from this corner to the opposite corner. Obviously, you can only lay until you get to the edge of a sheet, and then you have to make sure you're going across the roof to continue, right? So could you start at the bottom and run all the way across and then do all the way across the next layer? Sure, but you have to move your ladder more times, right? So you end up creating these kinds of little patterns that go up, and then you move your ladder and continue along, right? You do nail the roof, right, as you go along up here above, right, where the seam is. On a piece of roofing, there's usually a little line that tells you where you're supposed to nail. and you use roofing nails which have very fat, wide heads in comparison to the body of the nail, right, to make sure that it has a lot of surface area to hold that piece of roofing down. When we get all the way to the ridge, right, we can use some kind of a ridge vent if we want. So here's an example that I'll pass around of a ridge vent that has an asphalt shingle right top to it. We would have our asphalt shingles that would show up underneath. There's a tiny little bit of one in the corner, so if you look carefully you can see it. And then this is applied over the top of the roof. Notice there's a gap in the sheathing, right, the sheathing, so that you get the air to be able to actually flow out through this hole. But this is a good way of kind of understanding how the roof cap would go. You can instead just have what are called ridge units, which are little folded pieces of asphalt roofing that are designed to be along the ridge that kind of cap off the top of the roof itself. Sorry, I'm scanning to see if I see one that's up. Sometimes they're up high, but I'm not seeing a ridge unit. Clearly, I have to just bring in a few of these so that we can actually pass them around, right? If we have a valley condition, we have a couple different ways that we could choose to deal with it. We can put in a sheet metal valley and hold the roofing back as we go along. This is really nice for collections of debris and stuff. If you're near trees and you want those leaves to be able to run off the roof easily, this is a good solution to that, right? We can weave the corners where we have one piece of roofing that goes up this way, the piece under, as we go up, the next piece would go over the top, and they're woven, right? The other example is we can take one side of the roofing and continuously wrap it, and the other side can become and cut, right? So there's slightly different looks to the corner in terms of what you're after architecturally, right? We can move into slate shingles, which I think I pulled a couple of examples. Yeah, here we go. So slate is delivered to the side, split and trimmed to size. So this is done ideally in a factory setting. It's easier than doing it on site because they're very, very thin pieces. Remember when we talked about stone a million years ago, we talked about slate naturally having little cracks in it so that you can actually split it into very thin sheets. That's what these are done. These have been gauged so they have the correct thickness to them. The edges have been chipped a little bit so that they have a little bit of taper. That's for the look of it, so it's not a perfectly raw, natural piece of slate. Likewise, it's been squared up very nicely. This piece, I think, has been broken a few times, and it's, I think, designed to go more like this, so it's a little bit different exposure. But you get the idea of what the material is. It is a natural stone product, so it does vary in color and look. The nail holes are typically already punched so that you can actually attach it. The nails are going to be attached up above so that the slate then, the next layer overlaps it and covers it. Yes, sir?
Some places are a lot thicker, so just be aware of the weight when you guys are buying.
Absolutely. Absolutely. This is a very heavy roof.
The guys out there hand doing it.
Yeah.
Especially the thicker ones.
Right. So that's the kind of thing to be very aware of. I mean, we talk about asphalt being very heavy, asphalt shingles being very heavy. Stone is significantly heavier than that, right? So you have to design your structure around that. It is a fairly fire-resistant, long-lasting roof. No surprise, it's stone. Stone is a naturally fire-resistant material, so that's a good thing. It is very, very expensive, which shouldn't surprise you much, right? First cost. But it's expected to last 60 to 80 years. My guess is it would last a lot longer than that if it's well maintained. So it's the kind of thing that you shell out a lot in the beginning, but it's going to last for a long time. Yes? Good question. So that's the kind of thing you want to be very careful of. There are places that you can walk on a concrete tile roof or a slate tile roof that are less likely to crack, but not guaranteed not to crack. And so you have to place where you're going to walk based on how the pieces come together, right, and make sure that you're only on certain pieces of it. It'll make more sense when I talk about a concrete tile because I have some examples where we can put them together. But you want to make sure that wherever you're stepping isn't where there's an air gap, right? It's where there's a direct contact between your shingle and what's below it, right? If you step in the wrong place, it is easy to crack them. Then you've got to take out a portion of the roof and slide a new shingle in, and it's a mess. Right? But it can be done. It can be fixed. Right? So you want to be careful if you're walking on it. Certainly. Yeah.
Is there like a place that you might not want to have slate, just for the environment?
You're saying like if it was in snow conditions or something? Not that I'm aware of. I think you can have it because it's not the type of material that's going to expand and contract a great deal. So you can kind of withstand the temperature extremes. I think the biggest barrier to slate is more the cost of it than anything else, and that it's certainly going to be a little bit grippier. So if you had huge snow loads and you wanted to shed the snow load, so your building wasn't supporting all that weight, you might pick something like a standing seam metal roof that has a nice chute to be able to get rid of the snow. So it's going to vary a little bit more based on that, but I don't think the material itself would have any limitations.
We'll have to fix the roof. They're putting on the lake snow.
Right. To try to help it shed.
Yeah, if it sheds snow pretty easy.
Okay.
If you don't want to go up there to shovel, you might have to play on it.
Yeah, exactly. You're relying gravity on gravity to do that. So anyway, this is installing slate on a roof. You talked about walking out on a roof and kind of how do you avoid cracking it and sort of thing. Special system here with scaffolding to allow you to walk on it. Notice he's being very gentle with how much weight he's putting in and trying to install this. Recognize that you also have to carry all of these slate tiles out wherever they belong on the roof, which is another big challenge of where do you store them. This is a relatively steep roof, not the kind of roof that you're just going to be walking around on. A 6 and 12 or a 4 and 12 walking around on is very reasonable. But if you start getting steeper than that, it's much harder. You're going to want these kinds of scaffolding to be installed so you're not going to fall off the roof, and you've got to deal with carrying those pieces to the right place. So clay tiles, right, is a durable roof material. Some are made of concrete to look like clay. They're heavy. They're resistant to fire. So I have a couple examples here of actual clay tiles, and then I have some examples of concrete tiles. Here's the clay tiles, terracotta in this instance. And this is just another example of that. So we'll pass these guys around. Obviously, when we get to these kinds of stone pieces, the concrete pieces, they're very heavy. They'll break if you drop them, so try not to drop them. Right? And so these are kind of the traditional, tile roof. We see a lot of this in California. It's pretty well suited to our climate. It's expensive first cost. It's going to last 30 to 70 years. All of these estimates on how long roofs last, when we get into the slate and the tiles and the concrete and that sort of thing, it's a lot based on how well you maintain it more than anything else, right? If you make sure it's free of debris, if you don't climb out on it and crack the tiles, if your flashings and stuff don't rot away or rust away, those kinds of things can make this last a lot longer, right? So if we're looking at actually how it's put together, this is not the concrete tile that looks like a clay tile. This is the actual terracotta tile. How do you lay it? You have, if we're looking at section, I apologize, this is a little blurry. This is out of the book itself. We have a couple pieces here that are boards standing on end, right? This little blocking allows you to attach the top piece of the tile. Then you're going to flip the tile to have the underside here, to have the pattern where it overlaps and underlaps. Does that kind of make sense? Right? And so if water were to fall, it's going to fall into this channel and run out. Right? And so you can tell if a roof is actually a true terracotta clay tile roof by this kind of a pattern on the roof edge itself. Right? If it's a concrete tile, it'll look similar, but it's slightly different. And I don't know if I have... This is the traditional concrete tile, so I'll leave this slide up while we talk a little bit about the terracotta looking tiles. So these are examples of concrete tiles that are meant to look like the terracotta tile. And so these are the kinds of things that are ridiculously heavy to pass around, but I will pass them around, right? And so this is a concrete tile that's made so that it looks, when it's on the roof, a lot like the terracotta tile that I was talking about. It has the pattern, so to speak, right? But this is designed as a piece of concrete. It's molded differently than those, and it has a little groove in it that allows these two pieces to come together and start to form what looks like the tile roof, right? And so this is more and more common because it's a little bit cheaper to make, right, than these actual terracotta tiles. It's also a little bit more durable, certainly if you're walking out on it. Notice that it's very similar to what we've seen there. It has a nail hole that's already punched into it, right? Usually they also have this little, and this works for the regular concrete tile that's square up there that I'll show you in a second. it has a little lip that runs right here, right? You see that little lip that's underneath? What you'll do is you'll put a board that runs across your sheeting at that point, which allows you to actually hook this tile over that board and it rests on that board. Then you'll nail it into place, right? A lot of times you don't necessarily nail all the tiles anyway, because if there's an edge condition where you want to be able to pull up one of the tiles, it's a little bit easier to pull it up. They're very heavy to begin with, so they're not likely to go anywhere, right? But these are the kinds of things where you can relatively easily take these off, check something on the roof, and put them back on, right? So they're not too challenging to work with. So these are obviously heavy, so I apologize, but if you want to see them, you get the idea. I will pass around. These are some examples, so you can kind of see some different colors that are available. These are a little lighter to pass around in the concrete tile realm. Another example here of concrete tiles. These are significantly easier to pass around because they're small sheets. And this is basically the same sort of a look where they interlock, right? And they work the same way as one of these big tiles does. It's just a different look to them, different texture on the top surface. Right, so I'll pass these around. You're welcome to take these out of the box if you want to look at them more closely. Hold on, let's get it back in the box. This one's a little heavier than that box. And so this has a different look. Again, very, very common in this area to use concrete tile roofs. It must be laid on the roof. There's usually a minimum steepness that's required for this. So you can't have too low slope of a roof because you need that to be able to shed correctly. It's always recommended by the manufacturer. This goes for any type of these shingles materials. Asphalt shingles, for example, usually the minimum slope is a 4 and 12 right, roof. So that's 4 inches for every 12 inches of run, 4 feet for every 12 feet. Right? It's just like too much math. We always stick to the foot, the 12, because it's a consistent measurement, and then the other one varies, right? So the last type that we'll talk about is architectural sheet metal. And these sheets need to be spaced close enough to secure them against wind, uplift, and to absorb expansion and contraction of the joints. I only have one real example of this here. So when I'll pass this around. Be careful of the edges. It's not particularly sharp compared to some of the other stuff that I've passed around, but I at least want you to be aware of the edges. The seams are designed to maintain water tightness, right? And the seams create a strong visual pattern, right, that could be manipulated by a designer. So where those little grooves and seams occur is something that can be considered. It's generally a pretty high first cost, and the book says that it lasts for, quote, many decades, right? That's a nice vague answer. Again, as with any of these roofs, it's a lot dependent on the maintenance and how well they were installed to begin with as to how long they're going to last. The material itself also varies depending on its thickness or its gauge. Okay? So in terms of metal types, we have a variety. Lead is the softest. It's easily formed. It was used a lot, but it's toxic, so we've kind of phased that out, as with everything that's toxic, right? Copper is non-toxic, which is good. It's relatively soft, and it has this really cool bluish-green patina when it weathers. People love to use it in salt environments because it has this patina that happens, and it's relatively resistant to that corrosive nature of the salt. So it's something to consider. It is very, very expensive. It used to be not as expensive as it is now, but it's very expensive. If you've ever bought like electrical wire or something, you realize how expensive copper is now. That's why people steal wire. So it's something to be aware of. We can use stainless steel or titanium. The architects think of things like Frank Gehry, but the concept is the same. It's strong, it's very long lasting. The problem is it's very difficult to work with because it's such a rigid, difficult material, right? It's very strong and very resistive. So a lot of, like, for example, these panels, right, if they have any curvature to them, they need to be pre-made in a factory setting. It's not something where you can do it on site. It generally is going to maintain a silvery whitish color. Zinc is long-lasting, but it ages to a very dark gray, kind of dull color. So it would be a zinc-coated steel, most likely. Right? There are other metals Most common, the one I passed around is a good example of this, is an aluminum metallic coated steel, it's aluminum, metallic coated steel. Thank you. So sometimes, the notes just don't stand out. The one that I passed around is aluminum, but it's coated with a special paint, basically, that allows it to maintain a variety of colors. Right. In this instance, I think it was a bluish green, but you can get it pretty much in any color you want. Ideally, that paint isn't going to chip or flake away off the surface of the metal. It's designed not to do that. So it's better than just taking a piece of metal and painting it, right? It's done in a factory, that sort of thing. You can get that coated steel roof, although it's most common that you're going to get an aluminum roof to begin with. So if you're doing something like that, chances are something like this is going to come to the building site, ideally, because you can make a continuous length piece of roofing without having to put seams in. And so whenever possible, this is a really good advantage. So the steel comes on a roll, right, gets folded by this die, much like we did with the corrugations in the light gauge steel, right, to make that decking. We're going to do the same kind of thing here. The roofing sheet is going to come out in whatever length we need it to be for the roof itself, right, which gives us a lot of flexibility in what we can make, right? And so we have a couple different ways of attaching it together. This is considered to be a flat seam metal roof. And if we look at it, we start with one edge of the roofing having a hook on it, right? We have another edge of the roofing coming in here, right? This edge comes over like that and hooks over it. We drive a nail through here, right? Then we take this whole piece, right, and wrap it with another piece that goes over. Does that kind of make sense? So we have these multiple pieces that are coming together to integrate to make this roofing. So if we were looking at this bottom, right, if water were to get in here, it would have to get up over that layer and around this and back over and down past this loop into that. Does that make sense? So it's trying to be very, very difficult to get through. Yeah.
That second picture complete. It's just that cleat.
It's just this cleat. Thank you. This is a cleat holding this into place, and then this is the piece that's going over the top of the cleat. Thank you. All right. The other option, which I'm more familiar with, is called a standing seam metal roof. And this is where those continuous sheets are particularly useful. And so instead of having these joints that happen here, it would be a continuous sheet running up the face of the building. And so in this instance, we have a piece of metal that's L-shaped, right? So one of these sheets has an L on either side, right? We have a cleat that's put in here that has the little nail that runs up in between the two. And then we have the opposite side L that comes in, right? Then we'll take and we'll bend these two longer pieces, the L, right, over on top of this piece, right there. Then we'll fold this whole assembly over one more time, and we'll end up with a seam, right? Well, of course it's cut off, right? So we'll end up with a seam, basically by the time we fold this over, that doesn't allow the water to get through because we folded that seam over. But it stays standing, so it stays having a little ridge down down each section of roof, right? We can do it where it's a little bit larger, where these seams are larger with a little batten, right? Where we have a little wooden batten that's in between the two, and we cap it and then fold over each of those. It's like the standing seam metal roof, but it's wider, right? So it has a slightly different look to it that can be advantageous. Okay, so we're going to take our break now. Sorry it went a little long. The next section will be a little bit shorter. So let's come back at 8:30, and we'll go from there.